Hello, welcome to a new chapter. I will start with exercise 1, but before doing that, I would like to tell you something about functional and functional derivatives. Remember that in the last class, Santi told you that if you have an action of a field defined by the integral over dt dx over the whole space-time of certain Lagrangian density of q dot and qx, in this case I will not treat the case with x and t explicit dependence. So before doing that, let me suppose we are working in one dimension, because all I will say, it can be applied in 4 dimensions. So let me simplify a little bit, and let's imagine you have x here, and instead of qx, q prime, where q is a normal function of x in 1 dimension, remember. So if you want to perform the variation of an action, this action, if you remember what Santi told you, is by definition the integral of LQ plus alpha eta, eta being a function of x, of course, q prime plus alpha eta prime minus the Lagrangian density of q and q prime. And after a while, he obtained something like this: the partial derivative of the Lagrangian density with respect to q minus the total derivative with respect to x of the partial derivative with respect to q prime. But remember also that this dx can be written as a partial x because there is no dependence on t on x explicitly in the density, in the Lagrangian density, alpha times eta of x. So if you perform derivative of the action with respect to alpha, what you will get is this. So far so good. And this parenthesis is now defined as a functional derivative of s with respect to qx. So is there a way to define the functional derivative directly? Yes, you can define the functional derivative of s with respect to, let me put qy here because there is a reason to do this. I will talk about this in a moment. This is defined by the limit when alpha goes to 0, 1 over alpha times s in qx plus alpha eta x minus the action in qx. But if this is the usual way that mathematicians define these kind of things, but in order to be more practical, physicists decided that it's better to put a delta here. X, let me make some space, delta x minus y. This is obvious because if you follow the same steps in order to arrive here, then you will obtain, or you will get here, a delta x minus y. So this integral with this delta gives you partial L with respect to q y because of this x minus y here. And remember, this is x and this is x. Because of that, you will obtain, or you will get this. So this is the practical definition in order to compute the functional derivative. By the way, for those who doesn't know what is a functional is a thing. Whenever you enter a function, when you perform this operation, it gives you a number. This is a functional. So let's do some gymnastics about this to see how it works. For example, let me see. Suppose you have an action of a certain, let me call f of x instead of q to emphasize that this is a normal function, the functions that you worked in college. I mean, functions from R to R. So let's suppose as an example that you have the integral over the space from a to b. I will get rid of this a and b for lazy reasons, but don't forget that there is a lower limit and upper limit. So suppose you have f prime square minus f square divided by 2. Okay, let's compute the functional derivative using the definition. This will be the functional derivative with respect to fy is the limit when alpha goes to 0, 1 over alpha, the integral over dx, the integral dx of 1/2 f prime of x plus alpha delta prime x minus y. This prime is important because there is a delta and there is a prime here, so the consequence is that there is a prime here. All this square minus 1/2 f plus alpha delta square minus the integral of this thing. So let's compute. The first thing we can do is join this integral in one integral. So this is going to be limit when alpha goes to 0, 1 over alpha, the integral dx, and let's see. Let's factor out 1/2 here. Okay, so we will have f prime square plus alpha square delta prime square plus alpha 2f prime delta prime minus f square minus alpha square delta square, okay, minus alpha 2 f delta minus f prime square plus f square. So we can cancel out this f prime square with this and this with this, and if you enter this alpha here, then this square vanishes, this alpha vanishes also, this square and this alpha. And if we set alpha equal to 0, then this term is going to disappear, this term also. So the final result will be 1/2 the integral dx to f prime of x delta prime x minus y, this minus 2f of x delta x minus y, and I can cancel this 2 with this 2 here. So let's see. The first term contains a prime here, so we can perform integration by parts, and then it will give you this minus with f double prime x delta x minus y, and this term remains the same, minus f of x delta x minus y. We can factor out delta x minus y. Sorry, this minus is only adding to this f prime prime. Okay, so finally this delta with this integral cancels out, so we finally have f prime prime y, because of this y, minus f of y. So let's see if it works, remembering that with Santi you saw that when you perform the derivative with respect to alpha, this must be the partial derivative of the Lagrangian with respect to q minus the partial derivative with respect to x of the partial derivative with respect to q prime. This is the functional derivative. So if L is 1/2 f prime squared minus f squared, this is going to be minus f, looking at this, minus the partial derivative with respect to x, and here we have f prime, so minus f prime prime, and this is equal to this, as we know it had to happen. Good, let's do another example, another important example. Suppose you have this. You enter phi of x and you obtain phi of x 0. I mean, suppose I don't know, suppose phi of 5. So if you introduce 3x, for example, then you will obtain 3 times 5, 15. So you introduce a function and you get a number. This is perfectly functional. Useless functional if you want, but a functional. So let's see with this definition what is the functional derivative of s with respect to phi y, or if you want the functional derivative of phi of x with respect to phi y. Okay, this is the limit when alpha goes to 0 of 1 over alpha. The functional evaluated here, or I mean this guy, plus alpha delta x0 minus y, because the variable here is the same as the variable here, minus the functional evaluated in the f of x, namely phi of x0. This term cancels this term and this alpha with this alpha, and this gives you delta x0 minus y. So I think I made a mistake, sorry. I should write 0 here because it's this, sorry. So this is a definition, and we have the property 1, if you want, that the functional derivative of phi of x with respect to phi y is delta x minus y. Okay, let's compute now the derivative of this thing square. Let's see. The functional derivative of phi x0 square with respect to phi y is the limit when when alpha goes to 0 of phi of x0 plus alpha delta x minus y square minus phi of x0 squared divided by alpha. So we will have phi x0 squared plus alpha squared delta squared plus alpha to phi x0 delta x minus y and minus phi x0 squared over alpha. So we can cancel out this with this square with this alpha, and this alpha also. When alpha goes to 0, this term cancels, and the final result is 2 phi x 0 delta, sorry, again, this is x0, sorry, x0 minus y. So the general thing, as you probably guess, is that if you have a functional like this, some function of g of x, 0, then what you get is property 2, the functional derivative of a certain function of phi x with respect to phi y is the partial derivative of g with respect to phi x times delta x minus y, because phi squared, the derivative with respect to phi, is 2 phi. This is an example of this rule. Let's talk about another important property that you must know, is what happens if you have something like that. Let me call this thing f, because the action is defined by means of an integral, and I think it's better to put another letter here in order to avoid possible confusions. So if you perform the limit when alpha goes to 0, 1 over alpha of partial mu phi of x 0 plus alpha partial mu Dirac delta with x 0 here, this times partial mu phi x 0 plus alpha partial mu delta x 0 minus y minus partial mu phi x 0 partial mu phi x 0. This is going to be this times this, which will cancel with this. So the terms that will survive will be partial mu phi x 0 times alpha partial mu delta x 0 minus y plus alpha partial mu delta times partial mu phi x 0. I think we're done, because this with this will be sorry, and this times this, but we will obtain alpha squared. With this alpha, it will remain alpha, and when alpha goes to 0, then it will be cancelled. So the remaining term, the survival terms, are only this. So alpha, this alpha and this alpha will be cancelled by this alpha, so here we are. So if you have this thing, the functional derivative of, if you want, of this thing with respect to phi y will be this partial mu phi x 0 partial mu delta x 0 minus y. And if you look at this, as Santi told you, it's the same, this contraction and this other contraction, putting the index upstairs and index downstairs is the same thing. So this is the same thing as this. So we will have a factor 2 multiplying. But if you are asking what the hell is this, you have to keep in mind that the usual thing is when you have an action defined as an integral over the whole space-time, and then you have this into this integral. And then when you perform the functional derivative of this action with respect to phi y, then you will have this integral, and this, once you derive this thing, you will have this. So now we can integrate by parts, and we will have minus this integral 2 partial mu phi of, sorry. In this case, this x0, this variable, is integrated over whole space, which I call x instead of x0. Sorry. If you want, you can write this thing without the x0, because this 0 is an auxiliary tool. So, as I was saying, yes, let's perform the integration by parts. There appears a minus here, and this derivative is now applied to this other object times the Dirac delta function, and then we can cancel this integral with this delta, and the final result is, as it had to happen, minus 2 partial mu phi of y. This is an important thing, and that's it. This is the functional derivative. You can put here property 3 if you want. But what happens if I have, for example, I don't know, partial mu of phi, partial mu of psi? I mean, another field or another function, if you want. What is the functional derivative of this with respect to phi? Why? Well, let's do it. This is the limit when alpha goes to 0, 1 over alpha, partial mu phi of x plus alpha delta x minus y, with the derivative, times partial mu of psi minus this thing. So we can cancel this term with this term, and we can cancel this term times this with this alpha with this alpha, and we will have the derivative of the delta times partial mu of psi, and if you want, partial mu of psi times the partial mu of the delta. This delta, by the way, is four-dimensional delta. The notation here is delta x minus y. In this context, when you are working in four-dimensional space-time, this is defined, or short notation, delta ct minus c time prime, ct1 minus ct2 times delta x1 minus x2, delta y1 minus y2, and delta z1 minus z2, knowing that x is ct1, x1, i1, and z1, a point in space-time, and y is another point in space-time, ct2, x2, y2, and z2. Z. So this is the property 4. As long as I need more properties, I will write them. So I think we are prepared to start the exercise.